Hello, welcome all. Good morning. Let me first thank the organizers for giving me this opportunity to share my knowledge on spin resonance spectroscopy, especially NMR and ESR spectroscopy, their principles and their applications in chemistry, biochemistry. In this part of this lecture, I will give and explain the fundamentals of NMR, basics of NMR and EPR, comparison of NMR and EPR, how they are related, what are their applications in structure determination of simple, complex, protein, peptide, dynamics of these molecules. Incandescent spectroscopy is broadly classified into two types, NMR and ESR. NMR deals with the nuclear spin resonance due to spinning motion of proton nuclei either clockwise or anti-clockwise like a spinning top. ESR deals with the electron spin resonance similar to nuclear spin resonance. It can spin, the electron can spin either in clockwise or anti-clockwise. NMR was discovered by two American physicists, F. Bloch, Stanford University, and E. M. Purcell, Harvard University. They were jointly awarded Nobel Prize for Physics in the year 1952 for the invention of NMR. ESR was discovered by Russian physicist E. Javaisky. It was discovered 1 year before the NMR. Let us now discuss the principles of NMR and ESR spectroscopy. What are the important properties of nuclei? What are the important characteristics of nuclei? Nuclei has mass, charge, and spin, nuclear spin. It can it can spin either in clockwise or it can spin in anti-clockwise. Due to this spinning motion, it develops, it creates a magnetic field. Any spinning charged body will produce a magnetic field and a magnetic moment, as you have studied in basic physics. As a result of this, the nuclei are NMR active. NMR active. But we'll discuss later, not all the nuclei are NMR active. Only certain nuclei are NMR active. Why? We'll see now. Next slide. And next, ESR spectroscopy is exhibited by compounds with unpaired electrons and transition metal ions, inner transition metal ions, or F block metal ions. While they were drinking beer and working in EPR instrument, they put the beer sample in NMR tube and they got nice peaks. Since then, chemists and biochemists use the NMR techniques for structural elucidation and other various applications. In this slide, we will see why only certain nuclei are NMR active. Not all the nuclei are NMR active. For example, carbon 12, oxygen 18, oxygen 16, they are all not NMR active because they don't have I value. The I nuclear spin quantum number is equal to 0. So the nuclei which possess I greater than 0 are only NMR active. There are certain empirical rules which gives the relation between mass number and atomic number Z and the nuclear spin quantum number. For example, if the mass number is even and atomic number is even, for example, here in the case of carbon 12, mass number is even. As you see, mass number is 12 and atomic number is 6. It is also even. Therefore, I equal to 0. Similarly, for helium, the atomic number is even and 2. Mass number is 4. It is also even. Therefore, I equal to 0. Okay, now let us consider mass number is odd. For example, C13. C13 mass number is odd and atomic number is even. In that case, I equal to 1 by 2, 3 by 2, 5 by 2, etc. For mass number even, hydrogen 17, mass number 14, mass number is even and atomic number is odd, then I equal to 1, 2, 3, 4, etc. So for nitrogen, I equal to 1. These are only empirical experimental rules to predict whether the nuclei are NMR active or not. These are all asked in common GATE or CSIR examination. These questions are asked whether the nuclei is NMR active or not. It is not a theoretical rule, it is an empirical rule predicted based on the observations. In this, we will see what are nuclear quadrupole moments. Nuclei with I greater than half will possess nuclear quadrupole moments in addition to nuclear spin magnetic moments. Because of non-spherical distribution of charges in the nuclei, the NMR spectrum of these compounds will give broad absorption lines. Because of the interaction of nuclear quadrupole moments and nuclear spin magnetic moments, it also affects the line shape of neighborly nuclei. It is further dealt in separately in NQR spectroscopy. A nuclei with the nuclear magnetic moment nu because of the nuclear spinning motion, as we have seen earlier, when the nuclei is placed in the external magnetic field V naught, there is an interaction between the nuclear magnetic moment and the applied magnetic field. As a result of the interaction of these interactions, the interaction energy is equal to minus mu cross B naught for NMR, for ESR E equal to minus mu cross B naught, where the nuclear magnetic moment is given by the expression Gn mu n I, where I is the nuclear spin quantum number. Similarly, for ESR, S is the electron spin quantum number, Gn is the nuclear G factor, mu n is the nuclear magneton, Ge is the Lande G factor, mu b is the Bohr magneton, where nuclear magneton mu n is equal to Eh by 4 pi mp. Mp is the mass of the proton and E is the charge on the proton. Similarly, for Bohr magneton, Eh by 4 pi me, where me is the mass of the electron, charge E is the charge on the electron, H is Planck's constant. Okay, now I can have values plus of or minus of because of it can spin either in clockwise direction or in anti-clockwise direction. Similarly, for electron spin can also in clockwise or anti-clockwise. Therefore, S equal to plus or minus of ms equal to plus or minus of mi equal to plus or minus of. Now on substituting I equal to plus of, on substituting in this expression, E of equal to minus gn mu n b naught 1 by 2, and on substituting I equal to minus 1 by 2, then minus minus plus gn mu n b naught by 2. Similarly, on substituting s equal to 1 by 2, you will get the um, energy of the I equal to 1 by 2 state. On substituting I equal s equal to minus 1 by 2, you will get the energy of the ms equal to minus 1 by 2 state. As you see, the energy of the mi equal to 1 by 2 is lower in energy, lower minus. This is higher in energy, whereas in the case of ESR, it is reverse. E, that is the energy of M equal to ms equal to 1 by 2 is higher in energy, whereas the energy of ms equal to minus 1 by 2 is lower in energy because of the negative value. Because of the above interactions, the energy level splits into two levels in the presence of magnetic field, applied magnetic field. In the absence of magnetic field, these two levels are degenerate. In the presence of magnetic field, because of the interactions, they split into two non-degenerate levels. With the increase in magnetic field strength, the energy of splitting increases. The energy of the splitting increases. Similarly for ESR. In the case of ESR, the energy of splitting is very much greater, not up to the scale, because of the Bohr magneton. Bohr magneton is inversely proportional to mass of the electron, here mass of the proton. Because of the high mass of proton, the energy of splitting is lower, whereas in this case, the energy of the mass of the electron is very much smaller. Therefore, mu b value is larger. Mu b value is larger. Therefore, the energy of splitting is also larger. Therefore, delta E from the previous slide, delta E can be calculated from the energy expressions Gn mu n B naught. The energy of separation is given by Ge mu B naught. In the case of NMR, radio frequency, radio frequency radiation is used to affect the transition between the nuclear spin states. Whereas in the case of ESR, microwave is radiation, which are of higher in energy than radio frequency wave radiation, are used to cause the transition between these two energy levels. In this, we will study about nuclear resonance condition. What is nuclear resonance condition? When the energy of the radio frequency radiation is equal to the energy gap, the transition between the nuclear spin states or electron spin states will occur. It is given by the expression energy gap between the two states is equal to, from the previous slide, Gn mu n B naught, and delta E is equal to h nu. Therefore, h nu equal to Gn mu n B naught. When the frequency of the applied radio frequency radiation matches the energy gap, or the precision frequency of the nuclear magnetic moment about the applied magnetic field, then there will be resonance condition satisfied. Each nuclei has a different nu value. Nu value is different for different nuclei because of each nuclei has got nuclear factor Gn and nuclear magneton. Similarly for ESR also. As we have seen earlier, the resonance frequencies are higher for ESR. That is, microwave radiation is required. Microwave radiation is of higher energy than radio waves. It is because of the gyromagnetic ratio of the electron gamma is 659 times higher than the nuclei. For the same field, for free electron, when it is placed in the magnetic field B naught 0.32 Tesla, the resonance frequency is 9.8 gigahertz. Whereas for proton NMR, when the same magnetic field is applied, the resonance frequency for NMR is 14 megahertz. The resonance frequencies or gigahertz is 10 power 9 hertz, whereas megahertz is 10 power 6 hertz. The resonant frequencies are very much higher for ESR because of the large gyromagnetic ratio of electron of small mass. Let us see what is Larmor frequency. It is the rotational frequency. It is the rotational frequency of the nuclear magnetic moments. Larmor frequency is represented by W naught. It is a rotational frequency of the nuclear magnetic moment around an external magnetic field. The Larmor frequency is directly proportional to the applied magnetic field. With the increase in applied magnetic field strength, the Larmor frequency increases. Therefore, W omega naught equal to gamma B naught, where gamma is the proportionality constant called gyromagnetic ratio or magnetogyric ratio. It is different for different proton, where omega naught is the Larmor frequency or angular frequency of rotation. In terms of linear frequency, omega naught equal to 2 pi nu, we know from basic physics. Omega naught equal to, it is the angular frequency, it is the frequency of the frequency, linear frequency. There is a relation between angular frequency and the linear frequency. Therefore, on equating these two, gamma B naught equal to 2 pi nu, nu equal to gamma B naught by 2 pi. So what is Larmor frequency? It is the frequency with which the nuclear magnetic moment precesses around an external magnetic field. In NMR, the nuclear spin states are degenerate in the absence of magnetic field, whereas in the presence of magnetic field, these two levels are split. With the increase in field strength, the energy of splitting increases, as you see here. So at lower field strength, lower radio frequency energy is needed, whereas, for example, at higher field strength, we need RF radiation of higher frequency, of higher energy are required. The advantage of using higher applied field strength is that the spectrum is more resolved at higher frequency, higher radio wave frequency, and higher field strength, whereas low resolution NMR is obtained at lower radio wave frequency and lower magnetic field strength. Here we will study about the NMR instrumentation. Based on the NMR resonance condition, H nu equal to Gn mu n B naught, the NMR spectrum can be obtained by two methods, either by varying B naught, keeping nu constant, or by varying nu and B naught as constant. In this case, the magnetic field is varied by keeping the frequency constant. In most of the NMR instrument, the magnetic field strength is varied by keeping the new constant fixed. Here I have shown the schematic diagram of the NMR spectrometer. What are the components present in it? What are the role of each components? For example, in this case, you have sample holder. It is spinning so that to generate homogeneous magnetic field, uniform magnetic field, that is very important. And it has magnet, electromagnet. Yes, north pole, south pole, electromagnet, and sweep coil. and sweep generator is used to sweep the magnetic field by pairing the magnetic field. Radio frequency transmitter is used to produce radio frequency waves, radiation of of frequency nu. It is transmitted to the sample perpendicular to the magnetic field, and the radio frequency receiver is the detector. Using the detector, the radio frequency is received, and the signal is amplified to get the NMR spectrum as shown here. What are the important parameters obtained from their NMR spectra or ESR spectra? There are three important parameters obtained from their spectra. They are chemical shift in the case of NMR, whereas in the case of ESR, G values. We'll see everything in future in further slides. Spin-spin coupling constant, J value. Hyperfine splitting A, it is expressed in Gauss, it is expressed in Hertz. We have seen comparison table. We'll see further. And the intensity of the peak, intensity gives the, for example, gives the number of types of protons. For example, methylene proton, in proton. Um, so we and the intensity also gives the concentration of the sample. The area under the curve will give the concentration of the sample. So ESR can be used as an analytical tool. NMR and ESR can be used as an analytical tool. As I said in the previous slide, what is chemical shift? It is represented by delta. We'll see now, if you consider a bare proton, if you consider a bare proton, there will be no shielding. There will be no shielding by electron. There will be no shielding by other nuclei. Therefore, the magnetic felt by the bare proton is equal to B naught. Whereas, in the case of proton in a compound or in a molecule, the magnetic field felt by the proton in a compound is less than the actual applied magnetic field. The applied magnetic field is B naught. Therefore, B equal to B naught minus BE, where BE is this shielding field due to the other nuclei and electrons present in the compound. Therefore, the magnetic field felt by the proton in the compound is less than the applied magnetic field. Is subtracted, shielding field is subtracted, or equal to B naught minus sigma B naught. Sigma B naught, that is BE equal to sigma B naught, where sigma is called a shielding constant. It is different for different types of protons because of the different shielding. For example, we have earlier seen the frequency, the NMR frequency for this is a reference compound gamma Br, for reference compound Br divided by 2 pi, and this is the formula relation between the NMR frequency and the applied magnetic field strength B. So in the case of reference compound Br, the field felt by the nuclei in the reference compound. This is a compound, the resonance frequency of the compound nuclei, and Bc is the magnetic field felt by the nuclei in the compound. Therefore, chemical shift is defined as nu C minus nu R divided by nu r. Nu c minus nu r divided by nu r into 10 power 6, that is in parts per ppm, because the nu c minus nu r value is very very less. It is multiplied by 10 power 6. Here we will see what is NMR reference compound. In general, tetramethyl silane TMS is used as the NMR reference compound. It is used to calculate the chemical shift of different proton, different nuclei by using the formula. Since we need to know nu r, the resonance frequency of the reference compound. In this tetramethyl silane, why this is used as a reference compound? What are the important characteristics of this compound? Because all the 12 protons are chemically and magnetically equivalent, therefore it gives single signal for these 12 protons with the intense signal. The intensity is very very high, so it can be compared with the other compounds, and it is very high shielded. Why the methyl protons are very high shielded? Because silicon is more electropositive than carbon. Therefore, silicon donates the electron more electropositive. Therefore, it donates electron to the methyl protons. Therefore, these, because of the large electron density, the methylene protons are highly shielded. Further, the advantage of using this tetramethylsilane is that its boiling point is very very low, and also it is very inert. Because the boiling point is very low, it can be removed and recovered when it is added along with your sample. The reference compound is added along with your sample. Therefore, because it is inert, it won't react with your sample compound, and also since the boiling point is low, it can be removed and the compound can be recovered. Here in this, we'll see what is low resolution NMR. In the low resolution NMR, the spin-spin coupling constant is not resolved. There will be no spin-spin splitting. For example, methanol. In the case of methanol, there are two types of protons. There are two types of protons, OH proton and the CH3 proton. This is the TMS reference compound, where delta equal to 0 for reference compound, because for reference compound nu r minus nu r, that is therefore it is equal to 0, delta equal to 0 in delta scale. And this is because of oxygen is more electronegative, it attracts electron pair towards itself, therefore it is less shielded. It is less shielded, whereas methyl protons 3.35 occurs at resonance frequency delta value 3.35, shielded compared to OH proton. Here, there is no spin-spin splitting. Spin-spin splitting, we will see further. This is, there are two protons, therefore there are two signals because of two different chemical values, proton and proton. Okay, and next in the at 60 megahertz NMR spectrometer. This is 1,2 dichloroethane. Here, the two methylene proton 1, methylene proton 2, they are equivalent. They are chemically equivalent and magnetically equivalent. Therefore, you will get only one signal for CH2, these protons with the high intensity, because there are four protons. If the number of protons is more, then the height of the signal will be high. Okay, this is the reference compound signal EMS. With respect to this, the chemical shift value is calculated. Here, this is 1 comma 1 dichloroethane. This is an isomer of this compound. If you look at this, if you look at the structure of this compound, as you see, there are two types of protons. One is methyl proton and another is CH proton. Okay, so proton, this proton couples with these three protons. Therefore, it will split in it will split into four signal n plus 1. We'll see further. Therefore, it is a tetrate quartet signal with the chemical shift value 5.89. For this proton this proton CH3, this corresponds to CH3 proton. It splits into doublet because of spin-spin coupling with these protons with this proton n plus 1. Therefore, 2 splits into doublet 1:1 ratio. Different protons in a molecule gives different chemical shift because the magnetic field felt by the different types of proton will be different. Therefore, the Larmor frequency is different. Therefore, they will occur at different chemical shift values. Here, I have given the different organic compounds with the different chemical shift values. For example, aliphatic compounds gives chemical shift values in this region. They are highly shielded, whereas acidic compounds, aldehydes, the protons are de-shielded. Therefore, they will occur at higher del values. Those protons which are shielded, they occur near TMS. The TMS, as we have seen earlier, the protons are highly shielded. Therefore, delta value is 0. Delta value is higher. That means they are less shielded. Therefore, shielding increases in this order. The different compounds will have different chemical shift values as shown here. Here, what is spin-spin coupling constant? It is represented by J. For example, let us consider a compound AX type. There are two types of protons. A proton with the nuclear magnetic moment mu1 and X proton with the nuclear magnetic moment mu2. Spin-spin coupling occurs due to the coupling between the magnetic moments of A and the magnetic moments of X. What are the characteristics of J value? J value is expressed in hertz. The unit of J value is in hertz. We have seen earlier. What are the important characteristics of J value? J is independent of B naught. With the increase in applied field strength, J value does not increase, whereas delta value will increase. Delta value will increase with the increase in field strength. The spin-spin coupling constant is independent of the applied field. Equivalent nuclei, for example, two methyl protons. There are three protons in methyl group. They are equivalent nuclei. Therefore, there will be no coupling between them. The third important property of spin-spin coupling constant is multiplicity. What is multiplicity? It depends upon the number of neighboring nuclei. For example, for proton, there will be n plus 1 peaks when delta is very much greater than the coupling constant. For example, we'll see here This is CH3 proton. This is methylene proton CH2. This is again methylene proton, and this is of type. This is of M type, and this is of A. Let's label this proton as A, CH2 proton as M, and CH2 proton as X. Okay. The chemical shift values, the center delta A for this proton, delta M is the chemical shift value for this proton M, and delta X is the difference between delta Mx is very much greater than the J value. For example, the spin-spin coupling constant is the spin-spin coupling constant. The delta del Mx, the difference between the chemical shift of M and X is very much greater than J. In that case, it will give n plus 1 peaks. It follows n plus 1 rule for proton I equal to 1 by 2. The general formula, for example, if it is I equal to 1, I equal to 3 by 2, this n plus 1 rule is not applicable. We need to use this general formula 2ni plus 1 for nuclei with the spin I. For example, for proton I equal to 1 by 2, then I, if you substitute in this expression I equal to 1 by 2, n plus 1, therefore n, there will be n plus 1 peaks. Let us consider this example. This proton, CH3 proton, couples with this proton due to spin-spin coupling. This proton does not couple with this proton. We'll see further. One three only one bond coupling, one three coupling, or appreciable. One five, one six, 1 7. They are not observed. Those couplings, long bond couplings are not observed. Therefore, CH3 proton couples with the CH2 proton. This is one type of proton, so it couples with the n plus 1. Therefore, CH3 proton occurs as a triplet. Triplet. And CH2, now let us consider this proton, CH2 proton. This proton C couples with the two of methylene protons and three of methyl protons, therefore 5. Therefore, n plus 1, 5 plus 1, 6. There will be 6 sextet signal is obtained for this M-type proton, and for this proton, this proton couples with this proton couples with this. Therefore, you will get triplet signal for this proton. This is the multiplicity. What is the multiplicity of this proton? Triplet. The multiplicity of this M-type CH2 proton sextet because of n plus 1 rule, 5 plus 1. As we have seen in the previous slide, the J coupling is negligible greater than 3 bonds. For example, I have shown here one bond coupling. One bond coupling. This is 3 bond coupling. 1, 2, 3. This is 3 bond coupling. It is negligible greater than 3 bonds. 1, 4, 4 bond coupling, 5 bond coupling are negligible. However, there is an exception in delocalized aromatic conjugated system because of delocalization. The J coupling is appreciable even beyond 3 bonds, even in the case of delocalized system. The intensities of multiplets are symmetric about the center. For example, the intensities of multiplets are symmetric about the center of the multiplets. The relative intensities of the multiplets, triplet or sextet is given by the binomial expansion. Binomial expansion a plus b to the power n. We will see in the next slide. The relative intensities of the multiplets in multiplet is given by the binomial expansion formula a plus b whole power to the n. How it is calculated? Now we'll see for n equal to 0, if you substitute n equal to 0 in this expression, then anything to the power 0 equal to 1. Therefore, it is a singlet. For example, TMS in tetramethyl silane, it is observed as a singlet. All the protons are equivalent. Now, if you substitute n equal to 1, then a plus b to the power 1, therefore a plus b. The coefficients of the binomial expansion 1 is to 1. 1 is to 1. For n equal, therefore, for n equal to 0, it is a singlet. It is expressed, it is shown in the form of Pascal triangle. N equal to 0, it is a singlet. N equal to 1, then it is the doublet. For n equal to 2, the expression is a square plus 2ab plus b square. The coefficients of this equation 1 is to 2 is to 1. For n equal to 3, 1 is to 2 is to 1. Similarly, if you put n equal to 3, then a cube plus 3a square b plus 3b square a plus b cube. Therefore, 1 is to 3 is to 3 is to 1. For n equal to 3, it is a quadrat. Multiplet peak is obtained. For n equal to 4, quintet, 5, and n equal to 5, n plus 1. Therefore, 6 lines or 6 peaks are obtained sextet. So using the binomial expansion and their coefficients, the intensities of the multiplets obtained. For example, for n equal to 1 singlet and n equal to 1 doublet and n equal to 2, this addition of 1, 1 plus 1, 2, and similarly 1 plus 2, 1 plus 2 gives 3, 1 plus 2 plus 1 gives 3, similarly 1 plus 3, 4. This is how the Pascal triangle is obtained from the binomial expansion formula. Here, what are chemically and magnetically equivalent nuclei? Chemically equivalent nuclei. Let us consider the example 1, 2 dichloroethane. There are two methylene groups, methylene protons. They are identified and they are identical, chemically identical, as well as chemically equivalent. And therefore, they have same delta value, chemical shift, same environment, chemical environment. Now we'll see what are magnetically equivalent protons, magnetically equivalent nuclei. In this case, both have same chemical shift. Both the protons have same chemical shift and also J coupling constant. Here they have only same delta value. Here the two nuclei have same chemical shift value and also coupling constant values. For example, in this molecule, the protons sees this fluorine and sees hydrogen. These are chemically equivalent. They have same chemical shift values, but they are magnetically inequivalent. They have different coupling constant values. Let us see the types of spin-spin splitting. There are three types of spin-spin splitting. Zero order splitting. There is J equal to 0. There is no splitting at all. First order splitting and second order or higher order splitting. Okay, now let us see zero order splitting. For a system, AB system, there are two types of protons, A and B. They are different protons. They have different chemical shift values. You see there are two chemical shift, two protons, but they are not coupled. J equal to 0. Therefore, they have singlet signal. Singlet signal for A proton and singlet signal for B proton. Okay, now let us see first order splitting. What is first order splitting? In the case of first order splitting, the delta, actually it is from delta del value is from here to here, is very much greater than the J value, very much greater than the, that is del delta by J is greater than 8, then it obeys first order splitting, n plus 1 rule. Proton is coupled, A proton is coupled to B proton, therefore doublet signal appears. Similarly, B proton couples with A proton, therefore you will get a doublet for B proton similar to A proton, and the coupling constant is given by here del delta by J greater than 8. In this case, a first order splitting is obtained. It obeys n plus 1 rule. Let us now see what is second order or higher order splitting. When del delta by J is less than 8, that is J value is greater. In this case, J value is greater than del delta. Here, del delta value is greater than J value. Here you see this in this case del J value is greater than del delta, that is del delta by J less than 8. In that case, it does not obey the n plus 1 rule. This we will study about pulse NMR. It is also Fourier transform in NMR. All recent NMR instruments are based on pulsed or FT NMR. Let us see now. It is very easy to understand. In continuous wave NMR, it is the old version, and RF radiation is used to affect, a radio frequency radiation is used to affect the nuclear spin transitions. Similarly, in EPR, microwave radiation is used to cause the electron spin transitions from ms minus off to ms plus off. We have studied earlier. Here, RF radio frequency radiation is used in pulse NMR. The radio frequency radiation is used in the form of short, quick pulse. Flash pulse is nothing but a flash of RF radiation. The principles of pulsed NMR and EPR are also very similar. In EPR, microwave radiation pulse is used, whereas in NMR, radio frequency radiation pulse is used. The advantage of NMR is that the advantage of pulsed NMR is that NMR measurements is completed in seconds, less than seconds, whereas in the case of continuous wave NMR spectrometer in older version, the the time it is time consuming. We'll see further. As I explained earlier, the continuous wave NMR, it is the old version of NMR instrument. It is time consuming. We need to take several scans. It will take long time for recording, measuring NMR spectra of for a single compound. If the intensity is very low, then we need to carry out several scans. Whereas in modern pulse NMR, the sample is excited by a single multiple pulses of strong radio frequency wave of range of frequencies. Then the free induction decay is picked up on a receiver. We'll see the NMR measurement is completed in seconds. This is very important. This time consuming, the continuous wave NMR, whereas pulse NMR, the scanning, the measurement is completed in a few seconds because we use NMR radio wave pulse of a range of frequencies. We'll see the principles of it in the slide. To understand the pulse NMR or pulse EPR, we need to know the what is magnetization, what is net magnetization. Let us consider electron spins either in clockwise spin or anti-clockwise spin. They are degenerate in the absence of magnetic field. They are all randomly oriented in the absence of magnetic field. When in the presence of magnetic field V naught, these electron spins or nuclear spins are oriented. For example, Mi equal to plus of is oriented in the direction of the field. They are lower in energy. Mi equal to plus of is lower in energy. Therefore, the it is more populated, more number of spins in the ground state. It is the anti-clockwise spin. Anti-clockwise spin, Ma equal to minus of. It is the excited state. The number of spins with Mi equal to minus 1 by 2 is less. The population is higher in the ground state. Therefore, on subtracting, uh, we will get the net magnetization. Overall magnetization is in the Z direction. At equilibrium, the overall net magnetization M naught is in the Z direction. The net magnetization is shown here. The net magnetization as shown here, the previous slide here. Okay, it is in the Z direction. It is in the Z direction. When you apply a 90-degree pulse, you apply a 90-degree pulse, that is pi by 2 pulse. That is when you apply rotating magnetic field, radio frequency field, perpendicular to the z-axis, that is through x-axis. It is tilted. The magnetic when you apply the pulse, radio frequency oscillating magnetic field, it is tilted along minus y-axis. This is plus y-axis. It is tilted along. Therefore, the two levels are equally populated. The two levels are when you applying the 90-degree pulse, the two energy states are equally populated. They are saturated. Now, when you apply 180-degree pulse, pi pulse, the net magnetization is tilted opposite, that is plus z-axis to minus z-axis. In this case, there is a population inversion. See, this is thermal equilibrium. The net magnetization is along the z-axis. On applying 180-degree pulse, the magnetization is tilted opposite to plus z. It is in the minus z-axis, minus m naught. There is a population inversion. Now, what is pulse angle? This formula is very, very important, asked in CSIR and GATE. Problems were asked based on this. What is pulse angle? This is the angle through which the net magnetism is tilted from the z-axis. For example, 90-degree pulse. This 90-degree pulse, and this is 180-degree pulse. Theta equal to 180-degree pulse. Theta is radians. It is directly proportional to the rotating, oscillating radio frequency field, magnetic field. It is applied along the x-axis. It is the pulse. It is the oscillating, rotating magnetic radio frequency pulse. V1. it will be given. And what is TP? TP is the length of the time of the pulse applied. How long the pulse is applied. For example, if you apply for long time, then it will be tilted to minus z axis. If you if you give if the length of the time of the pulse is very less, then it will be tilted by a 20 degree, 10 degree, etc. Therefore, the pulse angle depends on the the applied radio frequency pulse and magnetic field, and also on the length of the time of the pulse. What is population inversion? On applying 180-degree pulse, pi pulse, when the pulse angle is 180 degree, the magnetization, the net magnetization is tilted from plus z to minus z axis. At that time, the population of excited state and ground state are reversed. It is called population inversion. Whereas when you apply pi by 2 pulse, 90-degree pulse, the energy levels are saturated. There will be no signal.